today we're going to look at graphing exponential growth and word problems. So there's going to be 3 different formulas that you're going to need, and when you look at these word problems, make sure you highlight the variables that you're going to need and what each one of those stand for. So exponential growth formulas, we will look at a growth. So we're going to have a plus, and so we're going to have a general exponential is an a b to the x, where a is what we start with, initial, b is our growth factor, and x, when we talk about word problems, are usually time. So specifically, let's look at this first word problem. Buffaloes in the last 12 years has an initial population of 38. So that initial population is very important. And it grew by 7% per year. So look at words like grow to tell you if we have a growth or a decay. So this is an exponential model where the number of buffaloes will be n. A is the initial value, which is 38 deer in this case. The increase is, the percent increase is 7%, and we always write that in decimal form, so you have to put that as 0.07. So what we call as the model is we substitute in what we know, so it would be 38, 1 plus 0.07, raised to the x or t. So if we want to know how much we would have after 12 years, we're just going to punch our calculator. So again, get your calculator out, punch with me. When you punch your calculator, you'll want to use the exponential growth, and so you take your 38, 1 plus your interest rate, and raise to the x power. Since we have 12 years, we'll just put in 12. So you can't have half of a buffalo, so we would have in 12 years, we would have 80, probably 86 buffalo. As far as the graphing of exponential goes, to graph an exponential equation, we're going to put it in our y equals. If we graph 38, again, we can put it in just the way it is in our formula, put our x variable. If we graph this, we might be surprised that we won't see anything. So remember, we have to change the window. And the window, if we're talking about time, the window here should probably be 0 to 12 or 15 years. If we started with 38 buffalo, a good window here might be 0 to 100. So now when you get your graph, you can kind of do one of two things. You can pencil it in. You can hit second table and get some values here. You can see as the values are going up, the graph goes up rather swiftly. So when you're graphing and you're asked to approximate where we would get 53, again, just kind of hit trace, and we're looking for 53, and it looks like around year 5 we would find 53 buffalo. Another place that we see exponential growth problems is with money. That's a little bit more exciting. The formula is a little bit more complicated, but you can see it's an exponential equation again because the variables are in the exponent. So this is a formula that you'll need to know how to use and what each one of these variables stand for. So A stands for the amount left after an amount of time. P is what's called the principal. This is a accounting term that means what you start with. R is our interest rate. And again, this will be in decimal. And when we save our money, sometimes banks will compound quarterly, monthly, yearly, and this is the number of times that we compound. So there's some typical ones. If we're annual, it's once. If it's monthly, you compound 12 times. Quarterly is another common way that our money is compounded. Quarterly would be 4. And then there's one last variable, and that variable is T. T is the amount of time that your money is going to stay in the bank. Okay, so these variables are very important. Make sure that you know what each one of these letters stand for, and then I'll give you a word problem and we'll substitute in what we know. So let's take this first example where we deposit $2,900 in a bank account. We have pays a 3.5% annual interest rate, and we want to know the balance after 5 years if the interest is compounded monthly and quarterly. So a couple different things going on here. 2,900 is what we start with. The interest rate is very important. And these words here, compounded monthly or quarterly, tells us something very important. And then we have to look for how long we're going to save this thing. So the first thing I want to do is how to translate words into our math formula. So the amount of money that we'd have left is P is what we start with. 1 plus the interest rate. The interest rate needs to be in decimals. N, let's look back. N is the number of times that we compound. So if we're compounding monthly, this would be a 12. And then all raised to the n times t. So n is 12. 5 years is what we're saving for. So we're actually going to raise this to the 60th power. So make sure these are in your notes good, and then you'll go directly to your calculator. Make sure you punch your calculator in correctly and verify that you'll have the correct answer. So again, if you just punch it just the way you see it, you'll see that after 5 years, if you remain with those interests in your bank account, then you would end up with $3,453.73. If you want to find out what your balance will be after 10 years, then what we'll have to do is change our 60 to, instead of 12 times 5, 12 times 10. So we change this number to a 120. And again, the easiest way to do that on your calculator is to hit second enter, so you can get that formula back up and just change that exponent to 120. So if we leave our money in the bank for 10 years, we would end up with $4,113.20. Now if I just change the problem around a little bit, and now this time, instead of getting interest every month, I only get it 4 times a year, then our formula would just change around just a bit. We'll still start off with the 2,900. We still have the same interest rate, but now we're having number of times that we compound is 4, and then our power will be number of times we compound times our years, so we'll raise that to the 20th power. So again, it shouldn't surprise you that we would have a little bit less if we compound less. And those are the areas that you have to change your formula at. Okay, I'd like you to try this fourth example by yourself. Read the problem, see if you can substitute in everything that you need to do. Then punch your calculator and see if you get the correct answer. So A would be the principal. We deposit $5,000. Our interest rate, again, we always move it 2 places. What are we dividing by? Let's read our, compounded quarterly, so we divide by a 4. And then when we raise our power, find after 3 years, this will be compounded 4 times in 3 years, so we'll raise it to the 12th power. So again, when you use your calculator, just make sure that you punch in. You can punch it just directly into your calculator, just like you see it. But you have to raise that, you have to do that math when you raise it to the power. So again, if you've punched this out correctly, your final answer, when we're dealing with dollars and cents, always round to the nearest penny, which is the hundredth spot. So this 5 would make this 45 cents. Put your dollar sign always in front of the numbers.